Good afternoon, all. Am I audible? Please respond, ma.
Yes, ma'am.
Okay,
Yes,
thank you. Thank you. Okay, so last class we have seen about the basic computer organization, right? That was the second unit. In that, we have seen that we have one register, that is accumulator, which holds one of the operand, and several other registers like program counter, data register, temporary registers. These are available. Okay, so as part of instruction execution, these many registers are necessary for completion of one particular instruction execution. So that registers, how they are communicated with the help of common bus system, that we have already seen, and followed by instruction cycle and interrupt cycles. Okay, so how the instruction can be executed, that with the help of flowchart that we have seen. Okay, so about one instruction to complete its execution, there we concluded that it will generate several micro operations starting from fetch state, decode, followed by execution. In every stage, several micro operations need to be initiated, and those micro operations are performed by generating certain control signals, right? So those control signals are generated by using certain hardware components. We call that as hardware control unit organization, or else we can generate those control signals by writing control sequence. It's nothing but a code, control words, which are stored in control memory, by which also we can generate the control signals, by which you can complete micro operations which proceed for completion of instruction execution. Okay, so we have seen the two hardware units of control organization, control unit organization, hardwired and microprogrammed control unit organization. Okay, so in second unit completely we talked about a basic computer organization with a single register that was called accumulator, which is the register used by the programmer for writing his programs. Okay, it is only one register, accumulator, available for the user for implementing his programs. Remaining all are the registers, processor registers, used based on the stages for generating the required micro sequence of operations. Okay, right? So, and in that basic computer organization, we concluded that we have only one register, that is a processor register, which is accumulator, available for the programmer for implementing his applications. Okay, so but if you see, while implementing while writing any programs, the programmer or the user, he may need few memory locations or few storage elements. Okay, for storing a pointer or a counter. See, if I wanted to implement a counter or a loop, I need to initialize a loop counter by which it will be updated every time. Based on that, I will be doing certain operations and all. Okay, so I may require certain storage place or a memory locations which are needed for storing maybe pointers or counters, or sometimes written addresses, or maybe temporary results like any partial products. Okay, so that are happened during multiplication, any case. Okay, right? So I may need some storage place or a memory locations indirectly for storing all these values. Okay, so for this, if I refer memory every time, okay, if I refer memory every time for such applications, which is time consuming process. Okay, so the most time consuming activity is memory access in case of computer. Okay, so to make a convenient for the programmer, it is with not just a single register. If more number of registers are available, then he will use the registers for implementing his programs rather than memory locations, so that we can reduce the time here. Okay, for completing your program execution, the time can be reduced if certain a large number of registers are available for the user for implementing the program. Okay, so hence the concept of multiple registers were introduced in the CPU. Okay, so that is deal with your see completely in unit 3, which deals with the CPU. So with this concept, actually we came to know that the major components apart from ALU and control unit, register set will also come into picture. Okay, so what is the use of these multiple registers is for storing intermediate or immediate data during the execution of the instructions. Okay, used for writing your programs by the programmer mainly. Okay, so as we have a number of registers, now you may require to transfer data between the registers or between the other parts of the components, other components of the CPU with the register. Okay, so the data transfer may happen. Okay, you should facilitate that communication between the registers and between a register and other parts of the CPU, other components of the CPU. Okay, so to facilitate that, we require again a common bus system. Okay, so a bus will facilitate the communication between all these registers or with the register with other parts of the CPU. Okay, so that communication is explained with the help of general register organization. Okay, so when more number of registers were there, how they were organized to complete one instruction. Okay, execution, that is explained with the help of a block diagram. So this is what the general register organization. Is it visible screen?
Yes, ma'am.
Okay. So here a bus organization have shown with 7 registers with the names register R1 to R7. Okay, total 7 CPU registers are shown here. And this is what your ALU, arithmetical and logical unit. Now it performs operations between the registers. Okay, so rather than accessing every time a memory unit for your data element, now your data elements are available, operands are available now in the register. Okay, you have to select one among the 7 registers. Similarly, second operand again among the 7 registers, and those 2 operands will be supplied to ALU, which will execute the operation between the 2 operands. Okay, so to provide that communication, we have a common bus, right? So here 7 registers are connected via 2 multiplexers, right, to form 2 buses, A and B buses. Okay, so A bus is used to supply first operand, B bus is used to supply second operand. Okay, so either first or second operand is one of the registers. Okay, so I have here an 8x1 mux is available. 2 8x1 muxes are available. Okay, so for this mux, what are the 8 inputs means? 7 inputs are coming from the register outputs. Okay, outputs of 7 registers are connected as input for this 8x1 mux. Apart from this 7, sometimes you may get operand from an input device. So one input facility is also available directly. That input can also be connected here. Okay. So out of these 8 possible inputs, one is connected to ALU. One is provided for ALU as a first operand. Okay. So to select one among 8, I require a selection input, which is called SELA, selection A, which is of a 3 in. Okay. So because I have 8 possible inputs, out of which one can be selected with the help of 3 selected lines. So 3-bit information is required as a control input to select one out of the 8 inputs. So with that, we'll be getting first operand via A bus to ALU. Similarly, the second operand can also be any of the 7 registers, or it can also be an input device. Okay, so out of the 8 possible inputs, one can be selected and given to ALU via B bus, which can be done by using the selected lines SELB. Again, 3-bit selection control input is necessary for this max, for second 8x1 max, to select 1 out of 8. Okay. So after this, now we have 2 operands data available for ALU to perform the operation. Okay. So ALU now can perform any of the arithmetical or logical operation. Okay. So out of the n arithmetic or logical operation, one operation will be selected. Okay. So by using, again, few control inputs are required here to select one of the operation to be performed by your ALU. So which is given by the bits OPR, which specifies the operation. Here just 5 bits are used so that I can perform 2 power 5 different operations, around 32 different operations I can perform. So with the help of 5 inputs, I can perform 32, maximum 32 operations I can perform, out of which how many you are implemented in your ALU, that is completely based on the designer's interest. Okay. So it is not mandatory always that 32 operations are to be implemented every time. Okay. Out of maximum 32 operations I can implement. So out of which it is the designer's interest to implement how many. Okay. So out of the available operations, this operation control field will select one of the operation, and that will be performed between A and B. And now result is available on the output bus. Okay, this is again output bus. The result is available. So based on the instruction, sometimes your result you may wanted to give to output device, since it is already available on the output bus, so which can be connected to an output device. So, or else sometimes the result may be stored back to any one of the registers. Okay, so which can also be facilitated here. The same output bus is connected to the inputs of all the registers, out of which only one particular register corresponding load control will be activated based on the instruction. Okay. So based on the instruction that you have given, which will specify what is the destination register. Okay. So out of the 7 destination registers, one corresponding register load line will be activated, which can be done by using 3 to 8 decoder. Okay. So coming to the inputs are, it has to select one out of the 7. So with the help of SELD, another 3-bit control inputs for this decoder, see, based on which it will select one of the register. Okay. I think I'm clear. This 3 to 8 decoder is used for activating only one particular register corresponding load control signal. The whichever is the load control is activated, that corresponding register will accept the data available on the output bus. Okay, remaining registers will not update, they won't accept because their load control is not in active state. Okay, so by using these SELA and SELB, OPR and SELD, we can select the inputs and the operation as well as the output also. Okay, so these are SELA is a 3-bit control input, SELB is also 3-bit control input, and SELD is also 3-bit control input based on the number of registers that you have. I have now implementing 7 registers, so 3 control inputs are sufficient for my operation. Okay, if I am using 16 registers, I may require 4 for each. Okay, right? That's what general register organization, and whatever are the remaining bits that I will dedicate for specifying the operation. So here for operation, I have dedicated 5 bits. Okay, right? So once you have fetched your instruction and after decoding, you could know that what is the operation and what are the operands. Okay, where are the operands? Nothing but in which register your operands are available. Operands is nothing but the numbers and which a particular operation you want to perform. Okay, and after performing the operation, where is the destination? Destination, is it an output device or is it a register? Okay, so everything will be available in the instruction. After decoding stage, you have to generate the required control signals for selecting SELA and SELB and OPR and SELD. Okay, so with which I can form some group of bits that will select what are the inputs and what is the operation as well as what is the destination. Okay, so that group of inputs are, first group is SELA. It is a 3-bit, right? It is a 3-bit control input required for selecting one of the register, right? So I'm using this as if 0, 0, if SEL3 inputs are, if it is 0, 0, 0, I will select data from input to be passed to ALU via A bus. Okay, so if it is 0, 0, 1, I wish to select register R1 as first operand. Okay, if it is 0, 1, 0, I wish to select register R2. If it is 0, 1, 1, R3. Likewise, all the possible 8 combinations are used for selecting any of the register from R1 to R7 or any input also. Okay, so this is R5. 1, 1, 0 is R6 and 1, 1, 1 is R7. Okay, and this selection is also same even for cell B also. Okay, so the cell B, another 3 control inputs is same as the same selection. Okay, 0, 0, 0 input 0, 0, 1, R1, 0, 1, 0, R2 and so on. Okay, and next specify OPR, which is the operation. Based on the 5 bits, one of the particular operation can be done. Okay, so as I mentioned, it is completely designer's perspective. Okay, so he has to choose what are the operations that I can perform. Okay, so what are the instructions are facilitated for the programmer for this particular computer, what are all the operations that it can perform. Okay, so while choosing the operations, we have already seen the designer has to keep in mind that the concept is instruction set completeness. He need to add the arithmetical and logical operations, some of the branch operations, some of the input and output activities, okay, and some of the operations like conditional checking. Okay, so while observing all these things, he has to design the number of instructions that are facilitated for the user for implementing his applications. Okay, so that is OPR bits. And coming to cell D, which will select any one of the 7 register for accepting the output, okay, which will activate the load controls. The same configuration is also even given for SCLD, except 00. If it is 00, we are not activating any of the load controls. It means the output is activated. Okay, so for cell D, if cell D, if these lines are 00, we are using output device. Okay, output device for supplying the results, and in any other remaining case it is 0. Same R1 to R7 corresponding loads will be activated. Only one load, right? So you know how the decoder output is. If selected lines are 0, 0, 1, then D1 the input will be activated. So it is D0 to D7 lines are the decoder output. D1 will be 1 and the remaining all will be 0. Okay, so only corresponding register R1 load will be activated, remaining all will be 0. Am I clear? For all zeros, if all zeros, then D0 will be activated. We are not using that pin since output will be selected. None of the load controls of registers are activated. It means the result is your output device. Output device will accept the result. Okay. So, and this complete group of bits, we call that as a control word, because this will used for selecting the registers and the operation or the destination. Okay, so that is what called control word. Sorry. Okay, so this is what your control word, which includes 3 bits of SCLA and 3 bits of SCLB and 3 bits of SCLD and operation of 5 bits. Totally 9 plus 5, 14 bit control word is necessary to perform a micro operation, which is what called it is doing execution. Okay, right? Okay, so what is the stage that it is doing? Execution of your instruction. See, fetch decoding is over. After decoding, we came to know how to perform the operation. Okay, what is the operation and where are the operands and what is the destination, everything. So this control word is needed for this unit to complete the execution stage. Okay, so this will initiate one of the micro operation. So certain control words, if they are available in a sequential manner, so I can now go by a memory which is called your control memory. Okay, which can be done in which we have done in micro programmed control organization. Similarly, I can proceed also, right? So let us see in detail what are these selection bits, SCLA and SCLB and SCLD, and what are the bits that are given for OPR. Okay, so this is the control word, and example of the micro operations we will see. And this is the binary code. 00 means input. Okay, 001, R1 register is selected as I mentioned earlier. Similarly, 111, R7. Similarly, SCLB, and coming to SCLD, none of the registers load will be activated if it is 00. Result is accepted by your output module. Okay, and 001, the result is accepted by R1 register, because if it is 001, the R1 corresponding load control will be activated. Similarly, 010, R2 corresponding load control, 011, R3, and so on. Okay, and coming to OPR, ALU operations. So OPR selection lines, these are the operations that they have given. 0, 0, 0, 0, transfer A, 0, 0, 0, 1, increment A, 0, 0, 1, 0, add A and B, okay? 0, 0, 1, 0, 1, subtract A minus B, you wanted to do, decrement A. Here A stands for not the accumulator, A stands for A bus, okay? The value present in A bus, we are transferring, okay? And here we are incrementing the value present in A bus, okay? Right? 0, 0, 0, 1, 0 means add A and B components, subtract A and B, decrement A, perform logical AND operation between A and B, logical OR operation, logical XOR operation, complementing A, shift right A, shift left A. These are few operations for ALU. Okay, OPR bits performed in your ALU. Okay, see, for example, if I want to perform an operation like R1 need to be loaded with addition of the two register contents R2 and R3. Okay, for this operation, to perform this operation, what is the control word? Okay, what is the control word for performing this micro operation? Anybody can tell me now with this similar indication? Your control word should have 3 bits of SELA and another 3 bits of SELB and another 3 bits of SELD, which specifies the destination register, and after that the operation bits OPR, which is of 5 bits, and all these are 3 bits. With which can I have the numbers bits?
0, 0, 1.
Okay. SELA, first operand is R2, so it has to select R2, right? SELA and SELB are the two input registers. Okay, input registers are R2 and R3. So SELA should be R2 first. R2 contents have to be copied onto A bus as per the diagram. So first opcode is binary code is 0, 1, 0. Am I right?
Yes, ma'am.
So second SELB is R3. So you have to select R3. So it is 0, 1, 1. And the destination register is R2, R1, sorry. So it is 0, 0, 1. And operation, what is the operation?
Addition.
Addition. So this one you have to use. So OPR bits are 0, 0, 0, 1, 0. Right? So this is the control word for performing addition of R2 and R3 and storing it into R1. Okay. So you require mux A selector lines, mux B selector lines, and ALU operator selector lines, and decoder destination selector lines. Okay. So these 4 control selection variables need to be generated at the control unit. Okay. Right. And they must be available at the beginning of the clock cycle for performing the execution stage. Right. So these 4 control selection lines are selection variables. You can generate it by using a hardware or else by using like this control word sequence, which is stored in a control memory, which we call it as a micro programmed control unit. Any of the 2 ways you can generate the required control selection inputs. Okay. Right. And for the same case, let us see a few more examples of because how the available opcode operations are used not just for performing this. You can also perform similar other operations also, like a few more examples we will see. For example, if I want to perform another operation like R1, R2 minus R3, R2 minus R3, you have to select the subtract operation. Only OPR bits are changed, right? Let us suppose, are there any input activities available here? If you wanted to see, if you want to transfer contents of a register to another output device, okay, right? So is that available or not? If you wanted to see, let us suppose I wanted to transfer contents available in a register R2 onto output device. What is the control sequence it could be? What are the control word to perform this micro operation? Transfer of contents R2 to output device. Can you tell me? SELA, you require SELB, SELD, and OPR. What are the control inputs for SELA?
0, 1, 0.
010.
Yes,
0, 1, 0.
0, 1, 0. Okay, because R2 contents we are transferring on to destination is output. Okay, so first input is any of the 7 registers, that is R2 we are using for selected lines A. Okay, so everywhere we have a transfer operations with A bus, so you have to use mux A only. Okay, so for SELA is 0, 1, 0. And next, what about SELB?
0, 0, 0.
All
Zeros.
zeros.
Okay, so SELB we are not using right now because this we are transferring on to output device. So SELB is dash. Okay, we are not using SELB. Next, SELD is your output. Okay, SELD is also not any one of the register, that is also dash. Okay, so it means we will be using output only here. If none of the control none of the load line is activated, means output only selected. And what is the operation? It is all zeros.
All zeros.
Okay, so as it is all zeros, the operation SELB will be not considered as a control input because it requires a transfer A. Only the contents of A bus are sufficient. It won't involve B in here. Okay, so this is what the control word. It is just like 0, 1, 0 and all zeros. The control word is 0, 1, 0 and all zeros. Okay, so let us see another example. If I want to transfer the contents of input to output, what could be the control word sequence? Input contents we are transferring to output.
All zeros.
So first SELA will be input you have to select. So it is 3 zeros. And SELB will not be there. SELD will also not be there. And the micro operation is 0, 0, 0. So all zeros. Okay, all zeros. Last example. If I want to clear any particular register, How can I do? What is the control word sequence? Can we perform this operation?
Selection A, all zeros.
Selection A, 0, 0, 0, then it will select input. You don't know what is coming to input, but you have to assure that it is 0.
Subtracting same register.
Yes, you can do this way. Or else you can do logical XOR operation between the same. Okay. Right? See, if I select R5 as SELA and SELB, between the two, you can perform either subtraction or exclusive OR operation. Okay. So if I perform exclusive OR operation, SELA is R5, so which is 101, 101, and SELB is also 101, and SELD, the result of the operation will be stored back to R5. Result is obviously it is 0. That will be stored to R5 back. So SELD is also 101, right? And the operation that we are selecting, if it is XOR, then it is 0, 1, 1, 0, 0. Okay. So XOR is better than subtract, because subtraction requires the circuitry. What we have a logical operation doesn't require any hardware, like it is bit to bit logic. But subtractor, we require half adder, number of, based on the number of bits of your register, it is 16 bit, that many parallel adder or subtractor combinational circuit you require. But for logical, less hardware is implemented, so that the combinational delay is also less. Okay. So this is what the control word for implementing this, right? So by observing this, it is clear that you can perform many other micro operations which can be generated by the CPU, not just only these OPR operations available. Okay, right? So each micro operation will have certain control word, and mostly, as I mentioned, it can be stored in a program memory. We call it as a control memory. So in that way, I can implement the control unit which is required for your CPU to cooperate or to perform all the desired sequence of operations. Okay, so this is what general register organization. So if more than one register is there in the CPU, how the operations are performed. Okay, so that is explained here. Is there any doubts here?
No, ma'am.
So the same as illustrated as with the example that we have already seen, and example of other micro operations are this. Okay, so few of them we have seen. Okay, likewise, you can perform any micro operation. Okay, so many other micro operations also we can perform apart from the listed here. Okay, so next concept, one of the useful feature that has been introduced in the CPU is called stack. Okay, so stack widely used for executing your operations. So nowadays, most of the computers includes this feature, which is what called stack, which is also termed as last in, first out, right? So why the name last in, first out? Anybody have idea?
Because the last element
Only
that
one side.
Okay, so usually your stack is, if I compare it as a stack of trays, if I, the last tray that was placed on the top, it has to be removed or taken off first, right? A row of trays or else a bunch of trays, if I place it one after one, the one that was placed last have to be removed first. So the same operation is even implemented in a stack. So it is last in, first out. So the item that was stored first has to be removed. Item that was stored last have to be removed first. Okay. So a stack here in terms of computer is also a kind of storage device, mainly used for storing information, like in such a manner that uses last in first out principle. Okay. So when I come for a stack in a digital computer, we require a register that holds mainly an address register, which can be count only, which holds the address of the stack, which is, we call it as a stack pointer. Okay. So here in stack, the register, the only one register that used is the stack pointer, which holds the address of the stack, right? And the value here, it always points to top of the stack. Okay. The element that is held last, to that it always points. Okay. And coming to the stack operations, we have two operations in stack. First one is the operation of insertion. We can load data onto stack, that was called operation of insertion or push operation. And the second supporting operation is pop, which is nothing but the operation of deletion. Okay. We can delete an element from the stack. Okay. So these operations are simultaneously, they will perform while doing it, updates automatically the stack pointer or the pointing register. Okay. In any case, either operation of insertion or deletion, the stack pointer is updated automatically. Okay. So first we will see how the stacks were implemented in a computer. After that, with that particular stack, what we can do. Okay. So the stack usually can be implemented in two ways. One is a register stack or else a memory stack. Okay. So a register stack is nothing but it can be placed like some unified structure, a separate structure, so which is organized as a collection of some finite number of registers. Okay. So some n registers or n memory words are used and they referred as a stack. Okay. So it is completely isolated type of structure, which consisting of some n number of words, n number of memory words, or else a sequence of registers we will use for referring it as a stack. Okay. So this is the example for a 64 word stack. Okay. So these are the 64 words which have addresses start from 0 to 63, right? So 0 is the least location, 60 is the last location. And these sequence of 64 words are, now I'm referring it as a stack. We call this as a register stack. Okay. And coming to this, how the operations are performed onto the stack. So here a register, as I mentioned, SP, which is the stack pointer, right? This will hold the address of the stack that points to the top of stack every time. Okay. So SP holds the address of this stack. So what can be the address? How many bit register is my SP for this example?
64.
64 words are there. Okay, so 0 to 63 is the decimal addresses. In terms of binary, they can be, to refer 63, 0 to 63, totally 64 elements. It is sufficient to have a 6-bit register,
Bits.
right? So SP is a 6-bit register, which has stack addresses starts from 0, 0, 0, 0 to last element 6 ones. Okay, so a 6-bit register, we call that as a stack pointer, will point always the top of stack, right? And we have another register which is called DR. That's what a data register. This holds the binary data that has to be written into, or else if you read out from the stack, the DR will hold that data. Okay, right? See, during as I mentioned, the two operations during push operation, right? Your stack will be loaded with data. What is that? That data to be loaded is holded by DR. Okay, during pop operation, one element will be deleted from the stack so that the deleted element will be copied into the data register. Okay, so this data register will hold the binary data to be written into or read out from the stack. And we also have 2 more single bit, okay, single bit status bits. I can say them as a flag bits or a status bits, which indicates whether the stack is full or empty. Okay, so because these 2 status conditions are mandatory, right, which will avoid the override of a valid data. Okay, if your stack is full, you can't perform push operation. You can't insert a new element into the stack. If the stack is empty, you cannot remove any element because it is empty, right? So these 2 single bit fields, flags, are used for the programmer to perform a valid push or pop operation. Okay, so coming to push operation, if I mention how the push micro operations are designed with respect to stack. So you know your SP is always pointed to top of the stack, right? So initially, if I assume, so what are the initial conditions? Initial conditions, SP will be at 0. Initially, SP is at this location. It is 0 because there are no elements in my stack. SP is 0. And how these bits, full and empty bits? What about full flag? It will be 0. It indicates that a stack is not full. Okay. And another flag, it is empty. What about this flag bit? Right
1.
now, the flag stack is empty, so empty will be 1. Okay, so if for this initial conditions, if I want to perform one push operation, when the push operation is valid, first of all, whether it is initial or final, or in between, okay, whatever it is the case, whether you have to, so initially you need to say that this is a valid push operation. When can I know that the push can perform? The first and foremost condition is you have to check the flag full. Okay, if the full flag is 0, it means the stack is not full. You can perform the push operation. it says that the push operation is valid. It will perform the push operation. Okay. So the first condition should be checked, is full is equal to 0 or not. If it is 0, then only the push operation will do. Okay. So what the push operation is doing? Let us suppose my first element is A, something like A. I want to push on to stack. SP is initially at 0. So when it what are the micro operations for push are? In my SP will be first incremented by 1. SP is incremented by 1. So it goes to the location 1. And in that place pointed by SP, I am transferring the contents of DR. Okay. So you have to load your A in DR first. Okay. With the help of data register, the transfer is happening. Okay. In DR, we will be loading the element A. So these two are the micro operations for push. Okay. After push operation, you have to say likewise how many pushes it can accept. It can load till your stack is full. Okay. When can I know that my stack is full? What is the condition immediately? Okay. I have to check after push operation. Every time I have to check my stack pointer value. Whenever it reaches to some value, I have to make my flag bit called full as 1. Okay. When I will do this, what is the contents of SP, so that it says my stack is full, no further push operations it will accept. What are the contents of SP here?
63.
See, if as and when my SP reaches 63, I am pushing the new element. Okay. So SP reaches 63 and I am pushing my new element here, something like X. So at this stage, is it indicates that my stack is full? Anybody? Is it true? SP 63, is it correct? I have an empty location here, right? This is what my stack total is 0 to 63. I have an empty location here. So SP, if SP is 63, it is not a final condition for setting the full flag. Am I right? Because I have an empty location here. Are you agree?
Yes, ma'am.
Okay. So what is the valid contents of SP for setting full as 1?
SP equal to 0.
SP is equal to 0. See, initially your SP is 0. The conditions are full 0 and empty 1. If full is 0, then only one push operation you can do. So your SP is incremented first and then it loads the element. Okay. So here every time stack pointer is pointing to a filled location. Am I right? Okay. So first push operation, your stack pointer is here. If I want to store the next element, next push operation is proceeded by incrementing the stack pointer and loading the contents. So for that case, SP is at 2. Next element, again SP is incremented and loads the new element. Okay. So every time stack pointer is pointing to a filled location in this organization. Okay. Right. So likewise, I am incrementing stack pointer till 63 and I am loaded the last, next element, let it be X. Okay. After this, because there is still one more empty location, I will not made my full as 1. Okay. Now new push operation is happened. So your SP will be incremented after this. Okay. So there are 6 ones are there and it is incremented by 1. I'll be getting a 7-bit result with 1 and 6 zeros, out of which only 6 zeros will be loaded by SP because it is just a 6-bit register. So hence SP will rolls down here and it is pointed to this location and I am loading my last element here. As and when SP reaches 0, it means my complete stack is full. Now I can make my full is equal to 1. Okay. So what is the end condition here? If SP is equal to 0, then I have to make my full as 1. And I can make my empty as 0 because there are elements. Irrespective of this condition, if one push operation is done, I can make my empty as 0 because one push operation is done. Okay. So this is based on this condition. This is without any condition. This is the fourth point. Okay. Is it clear?
Yes, ma'am.
Right. These are the micro operations that are performed for push operation. Initially, we will be checking the full flag. If full is equal to 0, then SP is incremented and then it stores the element. Likewise, if for every push operation, finally, whenever SP reaches 0, it means my stack is full. I can make my full flag 1 and empty is 0 at every case. Okay. Now, if you come for pop operations, see here what is happening every time here, a stack is growing towards incremental addresses. Okay. So here for every push micro operation, stack pointer is incrementing. Okay. So stack is growing towards incremental addresses, right? Now coming to pop operation. When you can perform pop operation. Either it is first or in between or last, when you can perform pop operation.
When it's in between and last.
Empty, the empty flag, if it is 0, then only you are eligible for performing pop operation, right? It's a valid pop operation. If empty is 1, it means stack is empty. There is nothing in there. Nothing is there in the stack to remove. Am I correct?
Yes, ma'am.
So if empty is 0, then only you can perform your pop operation. How the pop operation is performed? It is exactly reverse of push operation. Okay. See how what are the two micro operations for push? First stack pointer is incremented and then it copies. Okay. So the pop operation should be in a reverse manner, right? First, top of stack contents have to be transferred to data register and then stack pointer is decremented by 1. Okay, am I right? So first, top of stack pointer contents, right? So there's SP pointed contents are transferred to data register. Okay, and then you have to decrement the stack pointer. Okay, so if at this stage, if let us suppose C contents are transferred to C and then stack pointer is decremented by 1 to pointing to this element. Okay, right? So, but practically if you see, we are not deleting any element. It is as if like a pointer, we are moving down. If you, at this stage, if you do a push operation, stack pointer will increment and this location will be updated with the new contents. Okay. So these contents are overwrite. So it is not mandatory to clear these contents or to delete this element. Just copy this contents onto DR and then shift the stack pointer. This particular element will practically, it will not delete from the stack. Am I clear?
Yes, ma'am.
Okay, so this these are the two micro operations for pop. After this, So what is the last statement? When your empty flag will become 1? What is the condition here? If, so likewise, your stack pointer is decrementing as and when it reaches 0, it means there are no elements here. So if your stack pointer is equal to 0, during push operation, I will set my empty flag to 1. Okay. And my full as 0 always. For one every pop operation, my full flag will be 0 because one element have been deleted. The stack is not full, irrespective of whether SP reaches 0 or not. Full flag will be made 0 after one push operation. Okay. These are the micro operations for pop. Okay. So for push, SP is incremented by 1. And in that place, the DR contents are copied. If SP reaches 0, then I will make my full flag 1. Without any condition, my empty will be 0. Because it is not empty, there is one element available in the stack. For pop, these are exactly reverse operations. First, the transfer of contents from top of stack to DR. Sorry, this is SP. This is not DR. This is SP. My mistake. Okay. And then SP will be decremented. Okay. So in this kind of stack organization, the stack is growing towards incremental addresses. It is similarly, I can say that this stack is growing upwards. Okay. This is example for a register stack. As I mentioned, I can even use a set of memory place for defining it as a stack. That's what called memory stack. Okay. So if you come for memory stack, this total memory, out of which usually it is divided into 3 portions: program for storing your instructions, data for storing your operands, and stack mainly used for storing written addresses and all. Okay, any kind of element you can push on to stack, right? So likewise, your computer memory, nothing but memory stack means a portion of memory now can be referred to as a stack. Apart from a unified separate structure, which was done in case of register kind of stack. Okay. Right. So in case of register stack, we are using some standalone unit, separate unit with n number of registers to implement your stack structure. But in memory case, we can even implement, we can use a random access memory, which is connected to the CPU for implementing your stack. Okay. A portion of memory can be even referred as a stack, right? So here, how your program, which consisting of a sequence of instructions, to point those instructions, we have a pointing register, which is called a PC, program counter, which points to the instruction. Similarly, for data segment, data portion of your memory, which holds the operands, the address of the operand is available in another register, which is called AR. Similarly, the address of the top of stack is available in the stack pointer. Okay. So here my stack, for example, in this case, my stack limits I have taken 3000 and 4000. Between this, I have my portion of memory referring as a stack. Okay. So initially, in this case, example, I'm loading my stack pointer with the 4001. Initially, my SP is at this location. SP is 4001. Okay. So now I wanted to perform push operation. To push operation, these two are the micro operations that they have given. So first SP will be decremented by 1 so that it is pointing to the location 400 and some element is transferred here. Okay. So element available in data register is transferred to this particular location. Okay. So for the next push operation, again SP is decremented and the element is stored. Okay. If you observe here also, after the push operation, every time the stack pointer is pointing to an filled location. Okay, here also the stack pointer is pointing to a filled location, but the difference between register stack and memory stack here is the stack is growing towards decremental addresses. Decremental addresses. It's as if like it is growing down. I can say my stack is growing down. Okay. So every time stack pointer is incrementing and we are copying the contents. Okay. Sorry, decrementing. So the stack pointer is decrementing and we are copying the content. So here my stack is growing downwards or else stack is growing towards decremental addresses. That is the difference between register stack and memory stack. Okay. And reverse operations. So for pop, exactly, you are first the element pointed by top of stack is transferred to data register, and then the stack pointer is incremented by 1. Stack pointer is incremented by 1 because exactly reverse of push have to be done in pop. In any case, we won't have any flag bits like empty or full in case of memory kind of stack, which were available in register stack. Okay, as if like register stack, but memory stack doesn't have any flag bits like full or empty. Only we have to see the upper and lower limits, okay, which are available in some registers. You need to make them in a register by which you can observe whether the stack reached full or else it was empty. Okay. So this kind of memory stack is growing decremental addresses, and every time the stack pointer is decrementing by 1 and pushing the contents. Even here the stack is pointing to filled location every time. Stack pointer is pointing to a filled location. Okay. So this is another kind of memory organization. See, why can't I perform the push operation for SP incrementing? Means SP equal to SP plus 1 means there is no reason for that, because you can even organize your stack for this kind of architecture also. Okay. That is incremental memory stack. Okay. Or decremental memory stack. And you may get any doubt that why should I update the pointer first? I will place my contents first. After that, I will update my stack pointer. Why should not? Why I should not do that? Means there is no reason. You can even do that. Okay. So with respect to this, we have 4 different ways of organizing the stack. First updating the pointer, then loading the contents, or else you first load the contents and then update the pointer. If you do so, then the stack pointer will be pointing to a LMT location every time, because the first operation is copying the contents. Second operation is updating the stack pointer. Okay, in that case, it is pointing always a empty location. Accordingly, the pop operation will be do as like reverse. Okay, so likewise, if you can mix the things, so you can have 4 ways for organizing your stack. Am I clear? Is there any doubt here in my words?
Yes, ma'am.
Is there any doubt? Or else you are clear? What for S?
Yes,
I think I'm clear. So you have 4 ways of organizing your stack. Okay, so stack can be incremental addresses or decremental addresses, or it can be transfer first, after that update the pointer, or else update the pointer first, after that transfer the location. Okay, likewise, we have 4 possible ways. First case, I am saying for push operation, first I will update the pointer like incrementing, and then I transfer my contents. Okay, here stack pointer is updating. Or else I can implement my push like this. The stack pointer is updating first in any of the case, but it is decrementing. Okay, and transfer the contents. In any of the case, the transferring is happened as the second micro operation. So your stack pointer is always pointing to a filled location. Filled location. Okay. The third possibility, first I transfer the contents. After that, I will update my stack pointer. The fourth case, first I transfer the contents. After that, I will update my stack pointer as SP -1. Okay. In any of these 2 cases, the stack pointer is updating later. So SP is always pointing to an empty location. Okay. So this way we have 4 different kinds of organizations. So how your push has been implemented, similarly, your pop should be. Okay. So your pop in the first case, first transfer of the contents, it is exactly the reverse operation. So first DR should be loaded with the contents appointed by your stack. After that, SP will be updated. Since here it is incremented, so here it should be decremented because we have removed one of the element. Okay. Similarly, the pop operation in this kind of architecture should be DR, same operation, memory of SP, and your SP will be incremented because here it is decremented. So during pop, it will be incremented. Similarly, these 2. Okay. So first of all, while while designing your stack, the designer will fix any of these 4. And accordingly, the push and the pop micro operations will be defined either in the microprogrammed or hardwired control unit. Okay. So this is about stack operations. Stack and its operations. Now let us see how this stack is useful in case of a CPU for execution of operations and all. Okay. So I think you know there's notations, infix, prefix, and postfix notations.
yes, ma'am.
Okay, so I think you'd have come in C and data structures. See, this stack is widely used, very effective for evaluating arithmetical expressions. These are the 3 different notations available. A and B are the 2 operands. Between them, if you want to perform addition, if the operator is in between the operands, that is called infix notation. Okay. If the operator appears before the operands, it is called prefix or a Polish notation. If the operator is appears after the operands, then it is said to be postfix or reverse Polish notation. Okay. So if you have any simple arithmetic expression, right? For example, how the reverse Polish notation we can obtain means, since I have an operator in between these two, this is an infix notation. So how to convert that to reverse Polish notation or postfix notation? First, start by anyway. Here the operator's priority is first bracket. After that, multiplication or division, both are same. After that, addition or subtraction. Accordingly, so I have first an operand. In between these two, I have an operand. Okay, right? So you need to first take the two operands successively. After that, place the operand. Okay, so we have got one result operand and this is another result operand. So this is first actually converted to A star B. This is first number and the second number is C star D. In between these two, you have to perform addition. So this is a plus available. After that, convert this to RPN form or postfix form. This is AB star. After that, CD star. In between these two, you have to perform another addition operation. Okay. So this is what called reverse Polish notation. So once you have postfix notation or reverse Polish notation, how the stack is used for executing this means you have to scan the expression from left to right, right? So if whenever you have an operand, okay, this is your stack. If you have an operand, you need to push that operand onto stack. So I'll be placing first A. After that, second operand. So that also I will place. Okay. After that, star. It means an operator. Okay. You have to scan the expression from left to right. If it is an operand, we will be pushing that onto stack. If it is an operator, then we will perform two pop operations from the stack, and between those two, that particular operation is carried out, and the result of that operation is placed again onto the stack. Result is again one element only that is placed onto stack. Okay. After finishing that, next element is C, which is nothing but an operand that is again pushed onto stack. And the next element D, again it is an operand that is also pushed onto stack. And next we came up with an operator. So the two subsequent elements from the stack were popped out, and between those two, the operation is carried out. And the result is again pushed onto stack. So after that, our stack is with these two elements. First is already there, A star B, and the result of C star D will be stored as a second element. Okay. After that, again we have reached with one more operator. So the two elements from the stack are popped out, and between those two, the operation, which is nothing but addition, is carried out. So between A star B and C star D, the operator addition is carried out, and this result is pushed onto stack. Okay. Until you reach that there are no or more operands, till that we will be proceeding, with which we can evaluate any expression. That is the particular advantage of stack for evaluating any arithmetic operations. Okay. The same thing is explained with the help of some example 3, 4, 5, and 6. So first 3 is pushed onto stack because it is an operator, sorry, operand. After that, second element 4. And next we were encountered with an operator. So the two elements were popped out. Between 3 and 4, an operation which is multiplication is carried out. The result is 12. That 12 again pushed on to stack. After that, 5, which is again another operand. Again, it is pushed on to stack. After that, 6, again operand. It is pushed on to stack. After that, star, which is an operator. Between 5 and 6, the operation is carried out, which is 30. That is pushed on to stack back. And next, plus, which is again another operand operator. So 30 and 12, two elements are popped out from stack, and between the two, operation is carried out, which is addition, and the result is pushed on to stack, which is 42. So finally, at the end of evaluation, your stack will be with only one element, which is the result of that particular arithmetic operation evaluation. Okay. Right. So this is a stack way of organizing, which is used for implementing your applications or evaluation of simple arithmetic equations or expressions. Okay. So till now, we have seen 3 types of register organizations, right? One is in unit 2, which was accumulator based organization, right? Where we have a single register, which is accumulator only, which holds one of the operand, and the second operand is coming from a data register. Between the two, operation is selected and the operation is performed. Okay, that is accumulator based organization. And the second way of organizing the CPU is general register organization, GPR based organization, where we are using multiple registers. Okay, like from R1 to R7 as an example that we have seen. Multiple registers are used for holding the operands, and the operation is performed between them. Okay. And the third way of organizing the CPU is stack based organization. Here you don't require any register, only one particular register is sufficient, that is stack pointer, which is used for pointing the stack, and the total stack is used for evaluating the expression. But in case of RPN mode, reverse Polish notation is used. Okay, right? These are the 3 different evaluations of organizing the CPU or architecture of your CPU, right? See, in accumulator based organization, one of the operand is by default needs to be present in the accumulator. Okay, but see, you're in accumulator based, you require large memory accesses. You require more number of memory accesses, because the second operand or any other operands are completely available in the memory. You need to read the memory for the second operand every time via data register, right? So large memory traffic for every instruction that is there in the accumulator kind of organizing. Okay, using the stack based kind of organization, of course, you need to write your code effectively, because every time your expression should be in RPN mode, reverse Polish notation. Then only the stack way of evaluation is easy, right? So it is difficult to write efficient code for the processor. Okay. On the other hand, which is more familiar and useful or easier is the GPR organization. It provides the flexibility for much number of registers are available. Okay, so for the as the operands. So this provides a significant advantage while executing your instructions. Okay. So out of the three CPU organizations, the conclusion is GPR, general purpose register based organization, is advantageous when compared with the other two, right? So that's all for today. Next class we will see with the instruction formats. See, in single register, that's what basic computer organization, we have seen few instruction formats. The three different instruction formats available there are what do we call, memory reference, register reference, and IO reference, right? So there we have only one operand. By default it is in accumulator. The other operand address, other operand available in the memory, that address we are mentioning in the instruction, that is memory reference. The other two IO reference and register reference that we have seen. Now, if you come for general register organization, where I may have my operand in the register, not always in the memory. Okay, right? Okay, so in here, how the instruction format is varied. Okay, so in case of GPR, general register organization, the instruction formats are different. Okay, whichever are the common fields like opcode, address, and mode fields. Now here the address field is designates either memory address or a processor register also, not just the memory address. Okay, it can be even the processor register address also. Okay, so accordingly we will be having a different instruction formats, and according by whether based on your instruction, whether you are facilitating the address field to specify one register or else more than one register, accordingly I'll be having the three types of CPU organizations. In case of single accumulator register, this address field specifies only one operand, which is the memory address. Okay, in general register organization, this address field is responsible for specifying more than one register address, depending on the type of operation. Okay, so two operands for source and one operand for the destination. It can have a 3 register or 2 registers organization. Okay, and if you come for stack, the only one address that specifies the word, okay, address of the memory to be loaded onto top of stack, or else to be updated with the element popped out from the stack. Okay, so these are the three types of based on the three types of CPU organization, how a simple instruction is evaluated. Okay, so which can be explained in the next class. Anyway, it is a 2-hour continuity class, right? So till 3:30 I have, we will take just 10 minutes of break and we'll be back. Okay, so we'll rejoin by 2:50. Is that okay for you?
Yes,
Yes,
ma'am.
ma'am.
Okay, so by 2:50 we will meet again. So I'm ending the meet because the record it should convert, right? Okay. So we will join by 2:50 sharp. Okay, attendance will be collected at the end.